Welcome to Hart & Trocken. My name is Dirk Schiebon, and in this video I want to talk about continuity of functions. Continuity of functions usually means that we can draw the graph of a function without any interruption. That means without taking the pen from the paper. But as it turns out, the definition of continuity is a little more subtle and is closely related to the idea of the limit of sequences of numbers. So you want to know about that? Let's go! We motivate the following ideas by looking at the graphical example. This is the function f of x equals x squared, the normal parabola. We fix any point along the x-axis which we call x0. In this case, let us choose x0 equals 2. We then mark the function value of x0 on the y-axis. By adding lines, we illustrate how x0 is mapped onto f of x0. Now we choose a sequence of points, which we call xn, on the x-axis, which converges to x0. Now for each member of that sequence xn, we also mark the function value f of xn on the y-axis. And again, we illustrate the mapping process by drawing lines. Now, as I have told you before, we chose the sequence xn on the x-axis in such a way that it converges to x0. What we are interested in is the question if the sequence of function values of the members of the sequence xn also converge to the function value of the limit x0. Obviously, that is the case here for this function and that point x0. We can nicely illustrate that by animating the sequence. So the sequence starts here at the first member, and then you can see how it converges to x0 on the x-axis, and we watch what happens on the y-axis, and that also seems to converge nicely. So apparently that story works. That means if the original values xn converge to x0, that the function values f of xn converge to f of x0 is of course strongly connected to the behavior of the function, to the shape of the function. And it is quite obvious that that story is also working if we change the position of x0 along the x-axis. Again, that is due to the nice behavior of this function. And of course, that story doesn't only work for the parabola, but also for many other functions. For instance, for the very simple function fx equals x. And it also works if we choose other sequences converging to x0. For instance, a sequence which comes from below, that means from the left-hand side. Now let's see if we can find functions f where that story doesn't work out, at least for some specific bad points x0. That is the function f of x equals 1 over x. We have chosen the point x0 equals 1, and we see that the converging story still works out very nicely. The function values of the member of the sequence converge to f of x0 on the y-axis. But now let us closely observe what happens if the point x0 approaches the number 0. That means moves to the left. As you can see, the function value f of x0 moves higher and higher the more x0 approaches 0. But even though there is a little gap, the sequence of the function values still seems to converge to f of x0. We simply have to increase the number of the members of the sequence in our illustration. But what happens if x0 is exactly equal to 0? In this case, the sequence of the function values explodes. That means it goes to infinity. So it obviously does not converge to any limit. But anyway, there is nothing to converge to, because the function f doesn't even have a function value at x0 equals 0, simply because it is not defined at 0. So if we choose x0 to be 0 for the function 1 over x, our converging story does not work out. But we can destroy that story with much less effort. We simply have to be a little more creative when we define our function. This function, once more, is the parabola function. Well, not quite. Because with brute force, we redefined the function value at the point x equals 1 to be 0.5. That means the function behaves like the parabola function for every point on the x-axis except for x equals 1. Now looking at our converging story at x0 equals 1, we see that it does not succeed. Because the sequence of the function values approaches 1, which in fact would be the right function value if we had the perfect parabola, but of course it can't reach the value 0.5, which we have chosen by brute force. Now we are ready to write some things down, both for the function f of x equals x and for the function f of x equals x squared. We have observed that the following is true. Whenever we fix some point x0 on the x-axis and choose some sequence xn which converges to x0, the sequence of the function values f of xn converges to the function value of x0. That is what we have called a successful converging story. We can phrase that a little more catchy by saying that the limit of the sequence of the function values equals the function value of the limit of the sequence. In other words, a successful converging story means that we can pull the limit operator into the function brackets. We have additionally found that that works out for every sequence xn which converges to x0. It goes without saying that the function members xn need to be taken from the domain of f. Otherwise, there wouldn't be any function values which we could look at. Now, if we have a function where the converging game works out for every point x0 in the domain of f, the function values of the function change continuously. In this case, we call f a continuous function. We will specify what that exactly means in a minute. All points for which the above proposition doesn't hold, that means for which the converging game doesn't work out, are called discontinuities. So for instance, in our earlier example, the point x0 equals 1 is such a discontinuity. So let us now precisely define what a continuous function is. We first define what we mean by continuity at a certain point x0. So a function f is continuous at x0 if for every sequence xn which we take from the domain of f and which converges to x0, the function values f of xn converge to f of x0. And that is expressed by exactly the formalism we have already written down before. Now if we broaden that condition from one specific point x0 to all points where the function f is defined, we can say that the entire function f is continuous. So a function f is continuous if it is continuous for every x0 in the domain of f. Now the limit formalism we use here to describe continuity is precise but a little clumsy. In fact, there are two ways to write that in a shorter way. Here we simply say that the limit of fx equals f of x0 for any sequence x which converges to x0. In fact, that x is a sequence can only be recognized by the arrow notation below the limit symbol. This short notation even better highlights the fact that this condition must be met for any sequence x which converges to x0. If there is only one sequence where the converging game doesn't work out, continuity is destroyed at that point x0. Now a third way to express continuity is this. Here we say that the limit of f0 plus h equals f of x0, where h is any sequence which converges to 0. As h is a short way to address all possible 0 sequences, the sequence h may also converge to 0 from below, that means from the negative numbers. So let us summarize. For x to x0 in the above notation, every sequence xn which is taken from the domain of f and which converges to x0 can be chosen. Now, in fact, at discontinuities, funny things can happen with different sequences. For instance, if the sequences come from above or below x0. Let us, for instance, look at this piecewise defined function f. For all x which are strictly smaller than 0, f is equal to the parabola x squared over 4. For all other values of x, that means for all positive x including 0, the function is equal to the straight line x plus 1. Obviously, there is a discontinuity at x0 equals 0. That can easily be recognized because f has a jump at 0. We don't even need to look at the sequence condition. However, looking at sequences, we find that sequences coming from below 0, that means from the negative side, converge to 0. We see this even better by zooming in a little. On the other hand, if the sequence comes from the right-hand side, that means from above 0, the function values converge to 1. We can also zoom in to verify that. So for this point x0 equals 0 and this function f, all sequences coming from the right-hand side have a limit of 1 and all sequences coming from the left-hand side have a limit of 0. Now if these right-hand side limits exist and coincide for all sequences coming from the right-hand side, we call the function right continuous at x0. On the other hand, if all left-hand side limits exist and coincide for all left-hand side sequences, the function is called left continuous at x0. If we put that into formulas, a function f is called right continuous at x0 if the sequence of the function values for each sequence which comes from above x0, that means from the right-hand side, which can be also written like this, converges to f of x0. Similarly, a function f is called left continuous at x0 if the sequence of the function values for all functions coming from below x0, that means from the left-hand side, which can also be written like this, converge to f of x0. So what is an example of a function which is neither right nor left continuous? One example is this parabola where we redefine the function value at x0 by brute force to be 2. Obviously, neither the left-hand side sequences nor the right-hand side sequences are able to converge to the value 2. So this function is neither right nor left continuous. However, in this situation, if we like, we could continuously extend the function into the discontinuity at x0. To continuously extend means that we redefine the function value at the discontinuity in such a way that the entire function is continuous. In this case, of course, we could redefine it to be 0. In the case of the function 1 over x, at 0, the function values of all sequences which come from the right-hand side go to plus infinity. The function values of all sequences coming from the left-hand side, however, converge to negative infinity. So again, that function is neither right nor left continuous at 0. But here we need to be careful because there's a subtlety involved. Because do we need to care about the point 0 anyway? The point 0 is not included in the domain of that function, because that function is not defined at 0. So strictly speaking, the function 1 over x is a perfectly continuous function because the converging game succeeds for every x0 in its domain. The only point where it doesn't work is x0 equals 0, but that is not part of the domain of the function, so we don't worry about it. But also in this case, we can think about if there is a possibility of continuously extending the function into the point 0. So is there any function value for 0 we can additionally choose and thereby extending the domain of f to 0 such that the extended function is continuous on the entire x-axis? Well, the answer is there is no way to do that. This function cannot be continuously extended to 0. The simple reason is that the function values converge to either negative or positive infinity. A point where a function is not defined, like 0 in this case, is called a singularity. So let us now collect some examples for functions which are continuous on their entire domain. The first example are straight lines. Of course, the domain of a straight line is the complete x-axis. The second example is the normal parabola. The domain is also the complete x-axis. And the third example for an entirely continuous function is 1 over x, where, as we have seen, we have to exclude x equals 0, which is, however, not a problem because it doesn't belong to the domain of this function. Now, in many situations in mathematics, it is important to know if a given function is continuous or not. Because the sequence criterion for continuity is quite hard to verify in many cases, we need powerful rules to quickly decide if a function is continuous or not. Such rules are addressed by the following theorem. The idea behind this theorem is how we can build a new continuous function from two existing continuous functions. So let f and g be two functions which are continuous at the point x0. Then the following functions are also continuous at x0. F plus g, f minus g, the function c times f for any constant c, the function f times g, and the function f divided by g, where we have to ensure that that function is defined at x0, and that means that the denominator g of x0 must not equal 0. The proof of this theorem bases on the corresponding rules for sequences and limits of sequences, which we discuss in another video. And there is another part of that theorem addressing the composition of the functions g and f. If the function f is continuous at the point x0, and if the function g is continuous at the point y0, which is defined as f of x0, then the composite function g of f of x is continuous at x0. Note that it is important that g is continuous at f of x0 and not at x0, because it takes the output values of f as its input values. Now that theorem allows us to take two continuous functions and combine them in basically any way we can think of. The resulting combination will then also be a continuous function. So the theorem has the following direct applications. If the straight line function f of x equals x is continuous, then we can build the multiplication with itself and know that the result function f of x equals x squared is also continuous. Doing this repeatedly, we find that f of x equals x to the power of k is continuous for every k element n. From this follows that every polynomial is continuous, because a polynomial is built from power functions by multiplying them with constants and adding them up. Finally, rational functions, which are the quotient of two polynomials, are also continuous. More precisely, they are continuous for all x, where the polynomial in the denominator is not 0. Now let's have a look at some examples. We look at this piecewise definition of the function f. For x between 0 and 1, both included, it looks like the normal parabola, and for x greater than 1, it looks like the straight line 2x plus c. C is a real number which we can choose freely. Now the question is, for which values of c is f continuous? Let's have a look at the graphical illustration. This is the function where in this case the parameter c has been chosen to be 1. Obviously, the function f is continuous everywhere on its domain except for x0 equals 1. Which value does f have at x0 equals 1? Well, because 1 is contained in this piece of the definition, the value is 1 to the power of 2, which is 1. So the function value at x0 is 1. So obviously the function is left continuous, however it is not right continuous. To make it also right continuous, we have to change the value of c to make the jump disappear. So apparently the right value for c is -1. Let's have a look at a second example. Let f be piecewise defined by that formula. We first draw the graph of the function and then analyze for which x0 in the domain of f is discontinuous. And for the point where f is discontinuous, we analyze if it is even left or right discontinuous. So let's look at the graph of f. Apparently, there are 2 points of discontinuity. The first one is at x0 equals 1. According to the definition of f, the function value at 1 is contributed by the right piece of the function. So obviously, the function is right continuous at 1, but it is not left continuous at 1. The other point where f obviously is not continuous is -2. Because it obviously has a singularity at -2. However, the point -2 is not included in the domain of f. So even though things go wrong there, we don't care. At the end of this video, I want to show you one of the most famous functions when it comes to continuity. And that is the function f of x equals sine of 1 over x. Because 1 over x takes on very high values when x approaches 0, the frequency by which the sine function oscillates explodes as we get closer and closer to 0. So let's have a closer look by zooming in a little. So apparently things go very chaotic the closer and closer we get to 0. Obviously, the function value at 0 is not defined, because 1 over x is not defined at 0. Anyway, it is interesting to take a sequence on the x-axis, let it converge to 0, and watch what happens to the sequence of the function values of the sequence members. So let's do that. The function values of the sequence members which are thrown onto the y-axis don't show any converging behavior. In fact, it is very easy to prove that we cannot continuously extend this function to 0. The reason is that we can construct a sequence whose function values exactly target the peaks of the sine function. That means whose function values are always 1. The function values of such a sequence obviously converge to 1. But now it is equally easy to construct a sequence whose function values will be -1. Obviously, that sequence converges to -1. So the limits of the function values of different sequences will not coincide for this function. It can't be continuously extended to 0. So that's it for this video on continuity. Thanks for watching and see you next time.